Another important class of compounds are from Archaea, and they have a 3-carbon backbone and then 2 long chains of isoprenoids. These are 20-carbon structures here called phytonyl groups, and they're branched. They're long chains of carbon with branches every 5 carbons, and they can also come in a very long chain of 40 carbons, a biphytonyl. So this is a biphytonyl, and then you can have that attached on each end with an ether, so we call that a tetraether compound. And these are in the lipid layers of the archaeal cells, and these preserve geologic timescales pretty well, partly because they're just so darn big. They're not very degradable. And they're very famous in the paleoclimate community because they include some of our most important proxy tools. There's some example papers here. This is what's called the TEX86 ratio, and it's just simply the ratio of the different numbers of these ring structures varies with the temperature of growth in the environment. And so here's a sample from Antarctica versus Indonesia, and you can see the proportions of these really changes with the temperatures in those environments. So this is the TEX86 temperature proxy, and widely used and hotly debated, and keeps geochemists busy, sort of figuring out the nuances of this relationship. Another temperature proxy that's been around for some time is from long-chain ketones or alkenones that are derived from haptophyte algae that are famous for their coccoliths, which you can see here under the SEM. And these compounds are also very long, low solubility in aqueous solutions. So again, they tend to be preserved pretty well in geologic environments. And if they carry these double bonds with them, we can use them to measure temperatures in the past. And the way it works is that if you have more double bonds, it tends to be in a colder environment, and fewer, just 2 double bonds, tends to be a warmer environment. So the ratio of the 3 to 2 double bonds is a measure of temperature of the growth environment for these source organisms. And that's shown here. This is a compilation from Tim Herbert's lab, and shows the sort of ratio of the 2 to 3s changing here as a function of annual sea surface temperature from the global oceans. This is expressed in a very, I don't know, kind of a silly label. It's UK 37, so these are 37 carbons long, and it's unsaturated ketones is the UK. But this name was given to it by Simon Brassel, who is British and was working in a United Kingdom laboratory at the time. So there's a little nationalism sort of tucked in that name, just so you know. And if I go back to the TEX86, well, they're no less innocent here because they work at the Netherlands Institute of Oceanography, or NIOS, on the island of Texel. And so TEX86 actually carries the name Tex from Texel in it. So it's a little bit of a ping pong match as to who can name their proxy in the cutest manner. Okay, so this has no isotopes in it, but they're very, very important and very widely used. This is a paper that from Zhang's work a couple years ago now, looking across the eastern Pacific and the western Pacific Ocean at the gradients in sea surface temperatures from 12 million years ago until today. And here's the east and here's the west. So this side has kind of cooled, and this side has also cooled, but to a lesser degree. And this is the realm where we have the El Nino behaviors, and they're trying to test the hypothesis that 5 or 6 million years ago, 4 million years ago, was a constant El Nino state. And they're saying that that's not the case because they see this persistent difference with western side warmer than the eastern side, which is not a settled issue. It's an active area of discussion in the literature. But I like this paper because it illustrates both the TEX86 and the UK 37 data, and a really interesting and innovative application of it. I got interested in alkenones because they carry the carbon isotopes of the algae from the photic zone and preserve pretty well in environments. And so I think Brian, is Brian here? Yeah. Did you talk about PCO2 stuff a little bit? So I won't belabor it. But the idea is that we use that same understanding of the transport limitation to what we see in fractionation. is dying. Let's see if I can get this one to work. There we go. This fractionation here between CO2 and the cell, the biomass of the algae, varies with the supply of CO2 versus the demand and the inherent enzyme fractionation of that organism. And if we can kind of get a good sense of that, maybe we can reconstruct CO2. So we worked with alkenones to try and do that. And that model for interpreting that is very similar to what I began this lecture with. It's a transport, a two-step model with transport and then enzyme-driven fractionation. And the sensitivity to PCO2 is shown here. The fractionation factor varies with the amount of CO2 for kind of given conditions. And if you have changes in the growth rate or the demand of CO2, then that adds sort of another contour dimension to this problem. So demand and supply, as well as the inherent fractionation. But sort of on a large scale, you can see pretty sizable changes in fractionation if you have a big enough change in CO2. The other thing to note about this is that it sort of asymptotically flattens out as you go to very high CO2. So this method of CO2 reconstruction inherently is limited by that, and you can't reconstruct subtly changes at high CO2 levels. Yeah?
By the F2, does that mean the fractionation? What's the F2 mean?
Oh, that's interesting. That's a typo. That should be the flux of 2 to the flux of 1. Based on my earlier model. I apologize for that. So that's this ratio going in versus this ratio being of flow of material versus that flow there. So that should be, I think my Greek letter probably got confused when I was translating form, and then I corrected it incorrectly. So that's on me.
What is the F2 to the left of that? To the left of the
this is the ratio of 2 to 1. This flow 2 to flow 1, and it should be that's not a great subscript. We'll just call it F. And that's what I called it in the earlier slide. It's exactly analogous to the earlier slide that I showed you, just mislabeled. So we did a lot of work on this. This actually got started by work that John Jasper did with John Hayes way back in the late 80s. And then it got picked up, and it was done a lot in the sort of 90s, and then it dropped off. People got less interested in the technique, and it's starting to reemerge, and we're seeing more work using these compounds. This is some of the work that I was involved with. Mark Pagani, who was a grad student of mine and went on to a career at Yale, and he was able to chart out changes in that fractionation as a function of time on the million-year time scale, and argued that this change from about 35 million years ago down to about 20 million years ago is related to a change in CO2 during that time period. And then actually the biggest drop is sort of right in here, and then there's sort of another, then it kind of stays low. And this low value has been subject to some debate in the literature, and the people are beginning to revisit that, and they've kind of changing how they interpret that. We're not the only proxy in town, so there's other techniques that are applied. The red are the algae biomarker data, and then there's other methods, and in particular the stomata, which is changes in the sort of density of stomata on plant tissues, tracks the amount of CO2 in the environment. It's not a perfect proxy, but it shows slightly different character. And so this is the time period that's now being revisited with some of the newer alkinone techniques. So you didn't put a stake through the heart of it yet, Brian. It's reemerging. And all of this is to say that it's tied to these. Oh, this is Jim Zakos. This is a great picture. Does anybody know Jim? Yeah, you know Jim. Of course you do. Jim's a character, and he's like personally responsible for what we know about changes in detail in changes in oxygen isotopes in the world's ocean in the benthic realm, and has put together these curves. So now they're kind of called the Zakos curves. They actually had their start with Emiliani way back when, but he's really powered through the analyses to get kind of high detailed records. And there's a drop here in the values, and that's actually a cooling event. Some of this other drop here is actually the buildup of ice sheets. So it's not all simple ocean cooling, but the CO2 records that we're showing kind of match that drop in temperature with a drop in CO2. And the motivation here isn't just to reconstruct Earth history, which is cool in and of itself. But the motivation is to try and get a sense of how sensitive is our climate to changes in CO2, right? Because we want to make some predictions, and we want to know whether, we should be ringing the alarm bells or not worrying so much. Ring the alarm bells. But the idea is that we need a calibration of the change in temperature as a function of a change in CO2. So this is a term called the climate sensitivity term, and it's used in models that predict climate change. And it's a really important and not fully well-characterized term. So these are some of the feedbacks on different timescales from years to millions of years of the different kinds of feedbacks that can interact between temperature and CO2 changes. For example, the carbon cycle is sort of got this long one here. It can do all kinds of stuff. You can bury carbon or you can release it, for example. And another one, important one is the ice sheets, not the sea ice, but the ice sheets on land change the reflective properties of the world, and they can change sea level, of course, as well as they melt. And that's a slow, what's thought of as a slow feedback mechanism, as opposed to like clouds and water vapor in the air. That's a fast mechanism. So people are always interested in sort of time periods, or the response under slow conditions, and then the response under, the response under fast conditions and the response under longer conditions. The fast and slow together have a sensitivity of about 3 degrees Kelvin for a doubling of CO2. That's the Charney sensitivity, and that's kind of the default value that's in global climate models for predictive purposes. On longer time scales and at higher CO2, it's thought that these slow feedbacks, like the ice, goes away because the ice melts, and so you tend to have just these sort of shorter feedbacks, and the argument is that it's less sensitive on long time scales and high CO2. Paleoclimate studies will take issue with that, and they tend to argue that it's in fact more of these higher values and may even be higher than the Charney sensitivity. But I would caution you, in my opinion, we've used mostly marine data to figure that out. So we don't have a good climate sensitivity calibration using terrestrial environments. And so if you're looking for a place to make your mark as a emerging scientist, this is a big problem. It's sort of putting together the climate sensitivity in the terrestrial realm for these kind of modeling efforts.